This is the second part of Errors and Uncertainty. Part 1 comprises of systematic and random errors. The second part comprises of accuracy versus precision. To learn about part number 1 and part number 3, you can visit the link in the description. Right now, we're going to cover part number 2, which is to deal with precision and accuracy. What is the meaning of precision and accuracy? So first, let's keep it simple. Accuracy would simply mean, did you get the true answer or not? What is the true answer? Let me explain this with an example. And the answer of this question will always be a yes or no. It's going to be a binary answer. Now, for example, you're conducting an experiment to find out the value of G, which is, by experimentation, we know that this is 9.81. If a student repeats the experiment, it finds out that the value he or she is getting at that moment is 9.5, or let's say it's 10.7. Now 9.5 is a bit less than 9.8 and 10.7 is greater than 9.8, both of which are not presenting the true answer, which is 9.81. So in this example, the true answer is 9.81. Now ask yourself this question, is this the true answer? If this is, then it will be an accurate answer, or it will be considered accurate. If it's not, then it will be inaccurate. Simply moving towards precision. Precision also refers to the experiment that can you get the same answer if you repeat the experiment? Now, if you repeat the experiment again and again, regardless of the fact that was it accurate or not, if you're getting the same answer again and again, that means that that your setup or the experiment that you're conducting is precise. For example, a student carries out the experiment who was getting 9.5 again, and he gets the value of 9.6. He repeats again, gets 9.5, gets 9.7. Gets 9.4, gets 9.5. Now we can see that although the results are not accurate because we are expecting an answer of 9.81, but the student repeating the experiment is getting answers that are very close to each other, even if they are incorrect. So an experiment, or in an experiment, if the answers are close to each other and you get the same answer again and again, that means that your results or your experimental setup is precise. Of course, in simple terms, in O-levels or IGCSE, we can see that precision also refers to the least count of the experiment, that how precise, how closely it can get to the true answer. What is the smallest value it can measure? But in this context, we're talking about simply in terms of repeating the experiment. Can you repeat, and with confidence, and with 100% confidence, can you say that you're going to get the same answer? Now, in this set of values, we can see that with absolute confidence, I can say that I will get a value which is close to 9.6, 9.5, 9.4, 9.5. I may not get the true answer, but I have confidence in this that it will give me the same answer again. So this confidence deals with precision. 100% accurate answer gives me the confidence to say that I got the true answer, true value, right? So both accuracy and precision are going to be a binary answer. It's either going to be yes, or it's either going to be no. But of course, there are going to be a variable degree of precision. Sometimes one option may look more precise than the other, but to decide with absolute certainty, we need to do some calculations if you are in doubt. Again, these calculations are not a part of, you can say, a permanent solution to the problem, but they do help us figure out, or at least eliminate a few options that are going to make the question easy for us. So let's look at this first question. The question is from October-November 2004. And the question is question number 6. You can go back and check the marking scheme answer. Now, in this question, he gives you that a student or a group of students are repeating the experiment, or the conducting experiment to find out the value of G. Now, you already know the value of G, which is going to be 9.81. You already know that, right? So this will be considered as the true value or the accurate value. This is what we wanted to hear or learn, right? Now, student A has repeated the experiment 4 times, and up to D, everyone has done the experiment 4 times. So this was the result of experiment 1, this is experiment 2, this is 3 and 4. So they did the experiment 4 times, and this is what they got. This is what they individually got, right? Now, let's see what's happening. So he's asking us in the question, he's saying, which one of them, or which one of the students out of these 4 options results are precise, but they are not accurate. They're supposed to be close together, but they may get you a different answer, or may give you an answer which is not 9.81. Now let's see how to make this choice. Just by looking at the values, we can see this is 9.81, 9.79, 84, and 83. How do you decide whether they are accurate or not? Now, a simple way to do this would be just to guess. Now, of course, guesswork will help you eliminate a few options, but it will not give you the answer with certainty. Now, to have some sense of certainty that you're doing this in the most correct way possible, a good idea, again, this is just a technique. This is not a confirmed method. This is just a technique to eliminate the rest of the options. So what you do, you take the average of all the options for student A. So 9.81 plus 9.79 plus 9.84 plus 9.83 divided by 4, because these are 4 values. And I've done this for all the options. You can see that the average for the first value is 9.82, then 9.69, then 9.1, and then 8.46. Based on this data, I can precisely calculate, or you can say I can decide which one is going to have the highest accuracy, which one got closest to 9.81, which one out of them has done that. So 9.82, yes, it is accurate. 9.69 is not accurate because it is way off in comparison to 9.81. It's too far away. 9.1 is even further away from 9.81, and 8.46 is 100%, not a single chance that it is going to give me an answer of 9.81. So it is not accurate. Again, let's go back to the options. Do we get 9.8 answer in these options? No, there is not even a single option in 8 in this student D's experiment which gave us an idea that this should have been accurate or this may be accurate. No, it did not. So even if you didn't perform the average, even if you did not calculate the average, you would have decided, or you would have guessed, that this is not going to be accurate. The same goes for option C as well. This would not have been accurate because two values are 9.4, which is still less than, and 8.99, 8.76, less than 9.81. Again, this would give you an answer that this is not accurate. Same goes with student. Now, student A and B, by this guesswork, would confuse you, right? Now, to eliminate that confusion, the best way would be to take the average. Okay, again, this is one of the techniques. If I had to give marks out of all these positions, which one is the closest possible to 9.81? So the first position would go to 9.82. The second position goes to 9.69 because it is closer to 9.81 in comparison to the rest of them. The third position goes to 9.1, and the least accurate would be 8.46. Okay, or if you had to decide on the varying degrees of accuracy. Okay, let's move on to precision. What was precision? Precision was repeatability. Even if I'm getting the wrong answer, I don't care. But if I repeat the experiment, do I get the same answer? This is precision. Now for this, what we do is we calculate delta. Delta is the difference of the largest value minus the minimum value of the whole data set. So 9.79 is the smallest value and 9.84 is the largest value. If I subtract them, I'm going to get 0.05. I've done the same thing for the rest of the options. So the largest difference, or the difference between all the students, is 0.05, 1.18, 0.69, 0.09. If I had to give them marks, I can see that option A and D both are precise. They are very precise. Why? Because they have a very small difference or very closely related data values which are close to each other. They are not spread out. Let's look at it from their perspective. If I wanted to repeat the experiment, I would have very high confidence that I'm going to get the same answer as 8.5, let's say perhaps. I am confident about this. I know that this is wrong. The answer should have been 9.81, but my confidence that if I repeat the experiment, I'm going to get the same answer, this is precision, right? If I repeat the experiment, I get the same answer, precision achieved. Now, option A and D are very highly precise because if I repeat the experiment, the answer is going to remain the same, which is shown in value that they're close to each other. Highly imprecise, which are not precise, is going to be option B and C because there is a large scatter of points. If I repeat the experiment, it is highly unpredictable. Do I get something greater than 10 or do I get something less than 9.5 or 9 point something, right? Notice this is 8.94, which is much less than 9.5, right? So I am not confident. So the precision is low, so it is not precise. Now, if I had to give the marks or position for precision, this one would be the highest precise, this one will be the second position, this will be our third, and this will be the least precise. And the question was that it is supposed to be precise, but it is not supposed to be accurate. So first, let's see which options are precise but not accurate. So I'm only left with option A and D that are precise. So that eliminates option B and eliminates option C. So B and C are not going to be a part of my answers. That is for sure. But I'm also looking for highly inaccurate answers. I'm not looking for an accurate answer. So I have to make a choice between option A and option D. Option A is a precise student. The data was very close to, or the average was very close to the true answer. I'm not looking for this as it is mentioned in the question. So the inaccurate data with the highest precision is option D. So answer of this question will be option D. I've discussed the question in detail because you will encounter these questions again and again in terms of accuracy and precision. Okay, that's why I've spent a lot of time on this question. And similarly, from the topic 1 of the syllabus, this topic 1, our conclusion or summary was that yes, systematic error deals with accuracy and random errors deal with precision. Random error was we didn't know what's going to happen. It's going to be greater than or less than. Systematic error introduced a constant fixed error in all our data, right? So the systematic error affects accuracy. Random errors affect precision because they are highly unpredictable. And precision is all about prediction, right? We should get the same answer. Can we get the same answer? Moving on to the Archer example. Now, this is the most common example you will encounter in your books, in online videos, in online lessons. What is this example talking about? What does he want you to understand? So from an archer's perspective, of course, what he wants to achieve, what does he want to do? He wants to make sure that all his shots land at the center, which is in their language referred as bullseye, right? That you landed your shot at the very center, which is this position, okay? This is what they want to achieve, okay? This is what they want to do on a good day. Now, this begs the question, were they able to achieve what they were wanting to do? Did they do that? So first, the accuracy would define, did they get the center value? Did they land their shot at the center? It's a yes or no answer. So moving on to the results, what could be the possibility? So if he lands all his shots at the center, then of course, he is very accurate, right? Well, first, we will discuss accuracy and then precision. The second example looks something like this. He was able to get very close to the center. Was he accurate? Yes, he will consider it accurate because some of the shots landed at the center, some of them did not. So on an average effect, which we did over here in this example, we can see that even 9.69 or 9.70 rounded off was just shy a little bit from 9.81. So it could have been considered accurate, but again, it's an average value. So moving on to the third example. In the third example, we can see that whatever he did, he tried every single time and was not able to land his shot at the center. So he was not accurate. On the fourth example, again, he was unable to land a shot at the center, hence he was not accurate. Now let's decide about precision. Precision was about repeatability. Can I repeat the experiment? If I repeat the experiment, do I get the same answer? Simple question. So however many times the archer in the first example, in this example, did the experiment or took a shot, he always made sure he landed at the center. So he was precise. Yes. What about the second example? We can see that the shots are scattered. They're scattered left and right. So it is unpredictable that what the archer is going to do. So when there is an unpredictability, of course, the results are going to be not precise because they are not repeatable. They are not repeatable with high confidence. Can you, for this archer, take guarantee that when he's going to take the next shot, he's going to land at the center? You can't guarantee this. That's why he's not precise. Last, this archer, the third example archer, takes a shot and always lands at this point. For this archer, we can, with high confidence, predict that whenever he takes a shot, he always lands or he always comes to this side of the ring. So I can predict where he's going to go in the next or fifth shot. If I can predict, then of course he is precise. Similarly, in the fourth example, again, the shots are scattered everywhere. I cannot predict what he's going to do next. Since I cannot predict what he's going to do next, the archer is not precise. This is what the example of archer actually means. Was he able to get the bullseye? If he was, most of the times, then he will be considered accurate. And to put it into plain perspective or to simplify this results, if he lands at the center, he was accurate. If his data points are tightly packed, for example, they are tightly packed here, they're tightly packed here, then of course they will be precise because I can predict as an observer what he's going to do next. Over here, all the data points are scattered. I cannot predict what he's going to do next. I cannot predict where his shot is going to land next. That's why these results are not precise. So tightly packed points, highly precise. Scattered points, unpredictable, precision goes low. right? So this is the Archer example. This is what accuracy and precision looks like from that perspective. Okay, so from this angle, this is another perspective of the graph. This is another perspective from accuracy and precision calculation. Now, what does this graph actually mean? You see, you do an experiment, you conduct an experiment, and you do it again and again. You repeat the experiment to get the same answer, or to at least see what are the results going to be. So this is what that graph looks like. The y-axis represents the number of measurements. How many times did you repeat the experiment? And the x-axis represents the value that you were looking for. Now, for example, let's take the example of the gravitational acceleration. Again, which was 9.81. So the true value we are looking for is going to be 9.81. And now it's quite possible that sometimes you get value greater than that, sometimes you get it less than that. It's quite possible. So let's say that this is going to be, let's say for the sake of example, this is 10, this is 10.5, this is 11.0. And this is, let's say, 9.5, this is 9.0, and this is 8.5, right? Okay, moving on. So sometimes you're going to get value greater than that, sometimes you're going to get less than that. But how do you decide whether this is precise or not? So, for example, you conduct the experiment 100 times, and out of those 100 times, at least 50 times, you got 9.81, and a bit less than that. Let's say this is 9.7, and let's say this is 9.9. For the sake of example, how many times did you get 9.7? Probably 25 times. How many times did you get 9.9? Probably 20 times. So let's add them together. Let's say that this is 100. For the sake of example, you did the experiment 100 times, and out of those 100 times, you got 9.81 at least 50 times, right? So these results are highly accurate and highly precise, because the scatter of data, the smallest value and the largest value that you got are very close to each other, or you can say they are very close to 9.81, which is the true answer. So every time you repeat the experiment, you can say with confidence that you're going to get an answer which is between 9.7 and 9.9. The high confidence of prediction means that the results are precise. How do we see that on the graph? They will be tightly packed. They will be very close to each other. Similar example over here. If they're tightly packed, if they're close together, if the spread is small, then that is a precise answer. Similarly, let's discuss the rest of the example, the rest of the situations. What's happening in the rest of the examples? Okay, so that we can understand how to read these graphs. Okay, I hope that some of you might have picked out what these rest of the graphs actually mean, but you can pause the video and predict which graph seems to be odd. Okay, now we've discussed the green one. Let's discuss the black one, the black graph, right? Now, are we getting the true answer? Do we have a peak at the correct answer? Yes, there is a peak. This peak, there is a plateau on the true answer. So this is accurate. But is it precise? No, this is not precise. Why? Because the data is too much scattered. It is too scattered. And if it is scattered, my prediction, my confidence on the final answer goes low. Can I predict that next time I do the experiment, I will get the 9.81 answer? No, I cannot, because the range of answers is very wide. I can get answer high as 10.5 or as low as 9.0. I don't know. That's why the results are not precise, because they are not closely packed together. They are not tightly packed. Simple as that. So we understand this graph as well. Let's move on to the next, the red one. So we can see that the peak of our value is not at 9.81, although this graph goes to 9.81, but is the peak at 9.81? No, it's not, which means that this is inaccurate. The highest probability answer, the highest answer that got the largest number of answers is even less than 9.5. It could be 9.4, right? So the accuracy of this setup is very low. And are they precise? No, they're not, because again, the data is so scattered that I cannot give my prediction for the next answer, since my confidence is low in the precision or in the repeatability. The precision will be low. So it is imprecise and it is inaccurate. Let's discuss the blue graph. Now, since it is very close together, I can predict that this is going to be precise because the predictability is high. I know that the answers will not be out of this range. I can make the prediction with high confidence. Similarly, is the peak value at the true value? Is it giving me the true answer? No. Let's say it is 8.8. Is 8.8 actually 9.81? No, it's not. That's why it is not accurate. So I hope that we understand what questions to ask from a graph or from the question, and it will give you the answer back. Okay, let's look at an example that deals with these things. Another graph which combines the Archer and the precision and accuracy example. We can see in this example, the data is tightly packed, so it is precise. It is precise. And did we get the bullseye? Yes, so it is accurate. Precise and accurate. Now look at the graph. It is tightly packed and the peak value is at the highest value. Okay. Second graph, is it precise? No, it's not. The precision is low. Why? Because the data is scattered all over the place. But is it accurate? Yes. We can see that the average value or the peak value goes to the final answer or goes to the true answer. So it is somewhat accurate. Again, in comparison to the first case, it is quite low in accuracy. But on the average, when we take the average, as in the previous question, if it gets close to the true value, we will have to accept that in some sense this retains some form of accuracy. In this question, the data is tightly packed. So yes, it is precise, but it is accurate. Did we get them to the bullseye? No, we did not. So it is not accurate. That is why you can see that the peak value, this is your true value. The peak value is away from the true value. So it is not accurate. But are they close together? Yes, they're close together. So they are highly precise. Last example. Did we get the true answer? Did we get the bullseye? No, we did not get the bullseye. And we are much away. Our peak is away from the true answer. So accuracy is low. My data is scattered all over the place. So my precision is low, which shows up in the graph as a scattered graph. You can see that this is a bit pointy. This is a very slim graph, but this is very spread out. So precision is low. Let's see this question or see this example in action. So this question is from October, November 2002. It is exactly the same question. Now he says, which graph obtained of measurement x? Now x is the true value that you're looking for, right? This is the true value. It could be 5.0, could be anything. There is a large systematic error, but a small random error. Now, we discussed this example in terms of accuracy and precision. What are we supposed to do over here? Now, for this, from part one of the course, I've added a small summary over here for this question. And that is, systematic error is linked with accuracy, and random errors are linked with precision. So, he says large systematic error, which means low accuracy. It is not supposed to be accurate, which means that its peak must not be at x. I will choose a graph that peak is not at x. And with small random error is low precision. If the random error is low, it means that the precision is supposed to be high, which means that it will be a graph that is pointy, that has a less spread in comparison to the rest of them. Okay, so let's compare all of these four graphs. Okay, now do we need an accurate answer? There is a large systematic error, so let's add a small key over here. So this is systematic error and this is a random error. Systematic error deals with accuracy and random error deals with precision. Did we get the true answer as our peak? Yes, so it is accurate. So the systematic error is low. Is the data close together? Yes, it is precise. So the random error is low. Over here, example B. So what about systematic error dealing with accuracy and random error dealing with precision? Is it precise? No, because it is very much spread out. So the precision is not there, is low. So the random error is high. Did we get the true answer? Did we get the peak at the true answer, which is x naught? Yes, it is accurate. So the systematic error is low. Similarly, option C, dealing with systematic error as accuracy, random error as precision. Again, systematic error as accuracy, random error as precision. Did we get the true answer? Is there any peak over here? No, there is no peak. So there is a large systematic error in this reading or in this experiment. Is there a very small, tightly packed group of data? Yes, so the precision is high, the random error is low, right? Similarly, over here, did we get the peak at the correct answer? No, we did not. So the systematic error is high. And what about the precision? It is a very spread out data, so the precision is low. and random error is high. Let's follow the key. What the examiner wanted us to. So large systematic error. Can we choose this? Can we choose this? No. We needed large systematic error. So I need to choose an option in which the systematic error was high. So by this method, I can eliminate option A and B because I'm looking for a large systematic error, which deals with low accuracy. Again, and small random error, which deals with high precision. So I need small random error. The random error should be small with higher precision. So option C will be my answer, right? Again, I've discussed this in detail for you to apply this knowledge to the same questions exactly dealing with this idea. The next question is May June 2015, paper P13 or third variant is a bit difficult or is a bit more conceptual, but anyways, so 4 students do the experiment. Now notice what he has given you. He's given you the answer of 15.0, which means that this is going to be my true answer. 15.0 centimeters is the length of the pencil that I'm measuring, and this is my true answer. He says which experiments are precise but not accurate. They're supposed to be precise, but the accuracy can be accepted. The accuracy can be a way off, right? But we need precision. Okay, so looking at this data, we can see that the experiment has been done 4 times. Okay, so result 1, result 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So student A, student B, student C, and student D did the experiment 4 times, and these are their results. Now, how do you choose this? First, if you want to make a decision based on precision, just by looking at this and save time, I can see that the group should be close to each other. So if the data is closely packed, definitely they are precise. This is precise. Over here, the data is spread out. Over here, the data is spread out. So the precision is low. The precision is low. This is high precision. This will be high precision. And this will be low precision. The second thing he tells me, which one is going to be not accurate. Okay. Now, when I'm looking for an inaccurate answer, they shouldn't be accurate, I need to decide whether they got 15.0 or not. Now, again, to be absolutely sure about this, the best way or the best technique would be to take the average of all the obtained results. But just by looking at this, let's try to eliminate some options. Did we get 15.0 as a single answer? Yes, we did. Did we get 15.0 over here? So I can safely say that this is not going to be accurate because none of the data points are even close to 15. They are not. Now, this one also got 15 one time, so I'm not sure about this. Again, 15 and close data is very close data near to 15. So I'm unsure about student A, C, and D because some of them got 15, right? And D looks like to be a plausible option that it shouldn't be accurate. But let's see. Now, to put a final nail in the coffin, how to decide this is to take the average. Now, if you take the average of all the results, which is going to be very simple, simply add these measurements and divide them by 4. Now, student A average, this average is 14.47. This is 14.225. This is 15.0. This is 15.025. Right? Now, which one is going to be accurate? You see, we have to give them marks. Did it get the 15.0 which we were looking for, which is the true answer? Did we get that? No, we did not. Do we have 15.0? No, we did not. Do we have 15.0? Yes. Do we have 15.0? Yes. But if we had to give them marks or positions, this will be the first, this will be second, this will be third, this will be fourth, based on how close are they to 15, because 15 was our true answer. Moving on to the next point. We are looking for precision. Now, precision means the spread of data. So that is simply calculate the largest value minus the smallest value to see how spread out they are. So you can see that student A has a maximum spread of 1. And how did we calculate this? The largest is 15, the smallest is 14. So 15 minus 14 gives me 1.0 centimeter. So they're spread out by 1 centimeter. Again, this is 0.4, 1, and 4. So is this precise? No. In comparison to 0.4, they are not precise. Is 0.4 precise? Yes, it has. It is. So there is a tie between this option D and B in terms of precision. So this is precise, right? To give you the positions, this will be first, this will also be first, this will be second, this will be second. Now, again, now we have to make a choice between the accurate and precision. So he says they're supposed to be precise but not accurate. I can accept the not accurate, but they're supposed to be precise. Now, they're supposed to be not accurate, okay? So it is supposed to be either B, not accurate, not accurate is A and B, C and D are fairly accurate, but we are also looking for lower precision. Okay, so not accurate but high precision. So are they precise? Right? So option B is not accurate but precise. But which one of them is the closest one to the true answer? Right? So option D comes out on top. Okay, 15 is still closer to the true value but not entirely accurate. Of course, they are highly precise. You see, option B and D are highly precise. They have a small delta, they have a small spread out of data. But if I had to make a choice between 4.225 and 15.025, which one is closer to 15.0? Option D, 15.025, although still not entirely accurate. Why? Because I should have gotten the average as 15.000, which is this one. Again, this is a matter of discussion. This is a matter of understanding and acceptance that this is the true answer. This is going to be the correct answer based on these circumstances. Okay, I hope that we understand how to do this.